Hi friends, this is Chandrarao Kondapati, Director of Engineering Analog Layout Moschip. Today I would like to talk about analog layout introduction. Before I jump into the topic, let me introduce myself. I am Chandrarao Kondapati. I started my career into analog layout design as a trainee of analog layout in 2004 in 𝗂𝗽𝗺 Logic Limited, Hyderabad. After that, I served many positions in different companies as a lead manager, senior manager in 𝗧𝗦𝗔𝗧, 𝗧𝗦𝗔𝗧 Semiconductors and Moschip technologies. So today the agenda for this analog layout introduction is to bring you the details of analog layout, so that those who has completed graduation or diploma or M.Tech, they can select this as a career path to come into a analog layout. So without any delay, let me go to the agenda. So today I would like to cover what is VLSI, what it stands for, what is the analog design flow, and where a analog layout engineer domain stands, what are the challenges that we need to see when we do an entire flow, and also I would like to give a details about a fabrication and packaging and testing and the challenges in a VLSI design I am going to give it. And the finally I would like to give a details of what are the career opportunities available in analog layout, what are the eligibility criteria, how to get into analog layout domain. This is what I would like to cover today. I hope this is going to be useful for the freshers. They can to choose this as a career opportunity for them. What is VLSI? So everybody knows VLSI stands for very large scale integrated circuit. What does it mean? VLSI is a process of integrating thousands of devices, thousands of transistors, resistors, capacitors onto a single semiconductor chip. What are the places that we are using these ICs? So ICs are used in our day to day life applications, like you take smartphones, tablets, smart watches, televisions, and all householding appliances. Apart from this householding or the day to day life applications, there are many places we use these ICs in high computing, AI, telecommunications, image video sensors, healthcare, automobiles, consumer applications. Any circuit that you talk, any electronic circuit that you talk, without IC, we do not have any electronic circuits in these days. So with this, the ICs are becoming a more essential in a day to day life in all our applications. So it has a huge demand that there are many opportunities in IC designs and all those things. So agree, IC design flow is important, but why analog? Why only analog? So everybody talking about digital signal processing, digital circuits, and digital has a more accurate, more reliability result, less susceptibility noise and all those things, but still why analog? So what is our nature? The universe is in a analog format. Whatever you take, audio signals, video signals, and in fact whatever the voice that is delivering from me is an analog circuit. It is changing with respect to amplitude. So nature itself is analog, and all the microprocessors or the computers cannot understand the electronic circuits, electronic signals directly. So these electronic circuits form a bridge between analog nature to digital systems, and the analog is all the analog circuits cannot be understood by all the analog signals cannot be understood by microprocessors directly. We need to convert this analog into a digital format, and again the digital processing can be easier. I mean, as we discussed, I mean, digital has a like a fast processing and less susceptibility noise and all those things, but analog is essential as long as the universe and the nature exists. So, you cannot imagine without analog any nature. What are the analog circuits that we see, analog designs that we see? There are many analog circuits. I mean, I would like to give a few examples. Amplifiers are used to amplify the signals. So, comparators, voltage regulators, what is our electricity? Our electricity is like a AC format, but what our digital or the ICs or the analog circuits can take, I mean, all the circuits will take only DC signal, and any electronic circuits we expect or we should have a constant voltages, which is called a regulated power supply to our ICs, so that I mean it will produce the required outputs and all those things. All the regulated outputs can be generated from analog circuits using a voltage regulators, LDOs, BGRs and all those things. And there are many circuits operates with the frequencies. How to generate these frequencies? We need to have a clock generating circuits to generate frequencies, which you can call it as a PLLs, DLLs, where this generates a high speed clocks and all those things. And again, so as I mentioned, the nature is analog. I mean, all the analog signal has to be converted into digital, which where we need a analog to digital converters. And not only these, I mean, there are many analog circuits are there. I mean, there are like high speed transmitters, transreceivers, RF circuits to RF transmitters and receivers, and there are many other circuits in analog form still exists. Now, today talk about analog design flow. What is this analog design flow, where it starts and how it is finally fabricated and all those things, and also we will talk about each domain clearly, and we will see where our this analog layout represents why we need to understand other steps. So, any analog circuits that you want to design, so you need to have a defined spec. What does this spec has? Its spec has what is the application of the design that we are designing, what is the frequencies, what are the voltages that we are defining, and what is the expected outputs and all those things. Design specification is nothing but a electrical parameters or electrical definition of a circuit. Once you are very clear with the electronic circuit definition or a spec, you are ready to start the circuit design, which we call it as a schematic design. Once the schematics are designed, you need to simulate it whether the designed circuit is providing the expected outputs or the results are in line with the design specification that we have defined. If there are any mismatches between the results and the design spec, you need to go back and tune the circuit that you have designed. Say for suppose I mean the design is meeting the spec, then we are ready to start the layout design. You need to place the devices on a silicon, and you need to route them and all those things. We will talk in detail. So, once the layout is ready, you need to cross check whether this design is fabricatable or not, whether it is aligning with the schematic that we have designed, and you need to cross check if there are any mismatches, I mean that it cannot be fabricatable or it is not matching with the schematic, you need to go and tune the layouts. After that, I mean you need to cross check the simulations, whatever the design layout that we have designed, it is meeting our spec as per the design or as per the design specification that we have made. If there are again any differences, you need to go back and retune the layouts. Sometimes I mean you may have to go back to retune the circuit itself. Once the design is meeting all the physical verifications, post layout simulations, then we are ready to send for the fabrication. And once it is fabricated, you need to send it for the packaging to avoid the skip the physical damages from the outside, and the testing, and testing I mean you need to do the thorough testing in the labs, and if it is meeting on the silicon, I mean we can say I mean our chip is successful. What is mean by as design I mean spec, I mean we already defined a spec, now we need to design a circuit. The circuit design can be in a two layer I would say. One is the top level design, which is you need to define for a particular circuit what are the sub blocks that you will have. You can see a screen, there is a band gap circuit that we have defined, it has a op amp, it has a startup circuits, it has a PTAT and that circuit. So, we have defined as a block level circuits, that means it has a multiple blocks. So, that blocks connected interconnected I mean made a interconnections, so that it leads to a good spec that we have defined. Once the block level definition is done, you need to go through the each individual circuit design, where you need to design a op amp, you need to design a startup circuits, you need to design a CTAT, PTAT circuits. What is a circuit design? Circuit design is nothing but designing a circuit with the PMOS, NMOS, resistors, capacitors using a CAD tools, with we call it as a transistor level schematics. Okay. So, you need to understand the how to design a circuit, okay, that is a part of circuit designers who are going to design them, and again circuit designers are going to indicate the critical devices or critical signals which need to be taken care in a layout, and also they are going to define us what are the high current ratings, I mean what are any transistor is carrying like huge current, or any circuit or the any net I mean that we are going to see a low parasitics and all those things. So, it is a designer job to indicate the all the critical devices, signals, currents, and any other kind of criticality they need to inform us in a schematic with a some kind of notation. So, you can see a schematic of a op amp. If you see a circuit, I mean it is designed with a more than a 25 plus devices, where I mean lot of PMOSs, NMOSs are used, those are interconnected with to perform a op amp functionality and all those things. And if you look at the schematic, they have mentioned multiple times, multiple places, there is a critical circuits where we need to pay attention, that has to be taken care in layout, and also they are going to define the current values and the load capacitances and all those things. So, are we ready? I mean schematic is ready. Are we ready? I mean can we directly go and design the layout? No, we need to simulate the circuit or the schematic whatever the designers designed, and we need to understand whether it is meeting a spec defined. What is the, of course I mean you need to give the inputs, VDD supply, VSS supply, and you need to understand the whether it is giving the expected results or not. It is same as the lab I mean that we do in our academics, we connect the devices and we look at the results in the CRO or something like that. Once the schematics are meeting our spec or the required outputs, then we are ready to start the layout. So, before going to the layout directly, as a layout engineer, what all we need to understand from a design. So, we cannot directly go and place the devices and make the interconnections, we cannot say I mean it is ready for the tape out. You need to understand the design. If you understand the design, you can do a far better layout, because analog layout is like a art. I mean you do not have any predefined guidelines, the guidelines will change from circuit to circuit. You are going to design a layout, power FETs and all those things you define in a different structure, and high speed frequency circuits you define in a different structure. So, it is important to understand the schematic and understand the basic functionality, frequencies, power constraints, and we need to also understand the what are the critical nets that we have and all those things. You can identify the critical devices, optimize the minimize the crosstalk and the less impedance and all those things. It is not only important to understand the design, which will help you to do the design layout, it also helps us to debug the violations in a post layout simulation, so that we can go and easily fix the layout, so that it results in the positive or the with a high performance and all those things. Once you understand the design constraints and the design challenges or the expected what you call criticalities, you are ready to start the layout. How does a layout looks like? So, we know the symbol of PMOS and NMOS, and you can imagine the how cross sectional view of each device looks to be. If you take a PMOS, the P plus source and the P plus drain is isolated by a gate and gate oxide on a N substrate. If you look at the NMOS, a N plus source and the N plus drain are isolated by the gate and gate oxide on a P substrate. If you look at the top view of each cross sectional view, it seems to be like a P plus and N, P plus source and P plus drain are isolated by a gate material, where you can see on the right side the PMOS and the NMOS layout view of the PMOS and NMOS. So, all the PMOSs and NMOSs in the circuit, or the schematic that whatever the designer gave, will be replaced with the layouts of PMOS and NMOS. Here I have given a detailed layout of a particular PMOS, where you can see a multiple layers. You can see a active layer, N plus region, P plus region, and poly, metal, contact, and all those things. So, this is how a layout of a MOS transistor looks to be. It has a source, drain, gate, and source and drain, and gate has a contacts connected to metal, and of course, we have defined a bulk connection for this device as well. Layout to design. So, we understand the design functionality, frequencies, the critical parts of the design. Now, we need to start this layout. We know the layout view of a PMOS and NMOS. Now, we are ready to start the layout, and I would like to divide this layout to design into a two parts, where I will call it as a floor plan section, where we place the devices and make sure we have followed all the guidelines indicated in the designs, and also all the care that we have taken care in the floor plan itself. So, floor planning is nothing but a placing the devices close by, or the according to the guidelines given by the schematic, like critical portions and matching devices, what are the critical devices that we need to match and all those things. So, and also you need to make sure all the devices are placed such a way that it will have a smooth signal flow, and also it will offer a less parasitics, that means less routing between the devices, so that it offers a, in end results it offers a less parasitics. So, here I have given a one example of a critical devices, two PMOSs which are expected to be do a critical matching as per the design requirement. So, the floor plan of those two PMOSs I have mentioned on the right side, where we have done the matching and all those things. So, once the floor plan is done, we need to go back to the designer and get it reviewed with the designer, whether the placement of the devices are as expected as the designer expected, because whether the noise or the digital to analog noise cancellation using guard rings and all those things, whether we have taken care, or any other changes that the designer is expected, we need to get it reviewed with the designer. If the designer reviews and if he approves for the routing, we are ready to start the routing. Again, I would like to define the routing into a routing of MOS devices into a two parts. One, I will call it as a power routing, where all the devices which are connected to power and ground need to have a strong power connections, so that each device get the expected power, so that it can turn on into a expected regions of saturation region or the linear region, whatever the region that designer is expected, and also it pumps the enough current and enough voltages to the devices, so that it performs the well in the real time, which gives the better simulation results and all those things. And here you need to understand, as we discussed, we need to understand the power requirements of the circuit. Any high current devices or high power requirement devices we need to understand, and we need to provide the sufficient metal widths and number of vias and all those things, so that it reaches the maximum amount of the voltage and the current to the devices without any drops. Once the devices are routed with a power routing and we have provided the enough metal widths and all those things, we are ready to start the signal routing. So, signal routing is nothing but interconnecting the devices. We have in an op amp we have seen more than 25 devices. You can imagine there are many source, drain, gate, bulk connections. Those all has to be interconnected properly to make the functionality as expected in the design. While designing this signal routing, you need to have a clarity what all the critical signals, if there are any sensitive signals that we need to isolate from the noisy signals, you need to make sure you need to provide a proper isolation, and you need to provide the sufficient width of the metals to have the less parasitics and all those things, and the nets has to be routed as short as possible to reduce the resistance and all those things. So, here you can see a layout which is completed a floor plan, which has completed the power routing. You can see a VDD VSS in the bottom. All the gates are connected to, all the devices are connected to power and ground, and also signal routings are completed, and all the devices are completed with the signal routing and power routing. We can say this is layout is ready with the routing. So, once the layout is ready with the routing, we need to get it reviewed with the schematic designer. Again, there are any improvements that he is expecting us to do to reduce the parasitics or to meet the required functionality. So, can I say layout is completed with a placement, routing and power routing and all those things? Can we send it to the fabrication? No, we cannot send it to the fabrication. We need to cross check whether these designs can be fabricatable on silicon or not. So, why we need to cross check these DRCs? See, all the fabrication units uses a different methods to fabricate these devices, and it has its own limits. It cannot fabricate any rectangle or any via or anything, everything. So, they have defined or they have come up with a minimum design rules, where all these design rules must be followed in layout, so that this can be fabricatable. Say, if you do not follow this DRC rules, what will happen? So, if you do not follow these DRC rules, the designs cannot be fabricated. Even fabrication units may not accept these designs for the fabrication. So, it is must we should follow the minimum DRC rules, which are nothing but a minimum width, minimum spacings, minimum area, minimum enclosures and all those things. So, there are tools to do the physical verification checks, DRC checks, where it will represent if any of the metal or the drawings that we have drawn are not following the design specific rules, which we are call it as a DRC check. So, it will show us the minimum DRCs that wherever we did not followed and all those things. You need to go and correct the rectangle widths and the spacings and all those things, so that we can say it is a DRC clean database. Once this DRC is clean, can we say this again this layout is ready for the fabrication? No, the design is completed, routing, placement, routing and all those things, and it is DRC clean, but you need to cross check whatever the interconnections that we have made is as per the schematic or not. whether the correct devices are connected in a proper manner, or if there are any misconnections or the wrong connection, the entire function of the circuit can be damaged. Here example I have given a one layout versus schematic check, which we call it as a LVS, where it checks the connectivity of the each devices is done as per the schematic defined or not. If there are any mismatches, it is going to inform us in a LVS rules. Say example, you can see a inverter schematic where PMOS and NMOS gates are connected together and connected to a signal called A, but in layout we have intentionally made a one small wrong connection where PMOS source is connected to gate, where the gate and source are shorted together, which can result in a bad results. I mean, in fact, I mean the inverter will not act as a inverter here. The I mean, as we all know, inverter, when you give a 0, I mean you are going to expect that the output is 1, when you give a 1, I mean you are going to get a 0, but in this layout, since the VDD and gate are shorted together, you are going to see a different results than a inverter, where you will get always 1 0 as a output. So, the layout versus schematic is must to cross check. We met the designs, we have designed the layout as per the schematic, there are no deviations, there are no wrong connections and all those things. So, what will happen, I mean if we do not follow this LVS check, or if we say this layout is LVS not clean, if the design is not LVS clean, that can lead to a poor functionality or unpredictable performance, or sometimes the complete circuit collapse can happen, circuit can fail you. The designs are LVS clean, DRC clean, can we send it to the foundry? No, we need to cross check whatever we have designed is meeting our spec whatever we have defined in the starting. So, we need to do a post layout simulations where you need to pump the inputs and the voltages, we call it as a test benches. So, and you need to simulate the post layout, understand the characteristics of a output signal, whether it is meeting as the same circuit defined in the starting or the spec defined. If there are any corrections, I mean say for suppose if it is a deviation from the schematic results, you need to go back and tune the layout and you need to cross check again. Generally the whatever the schematic results and the layout designs may not meet immediately, because all the schematics are defined without any parasitic estimations and all those things, but here in real time we have a parasitics. Parasitics, what does it mean by parasitic? Parasitics are unwanted resistances and capacitances offered by the interconnection between the devices. So, all these capacitances or the resistors can degrade the performance. So, we need to design the circuit considering the parasitics. So, in practical whatever the parasitics that we see in the layout will be captured in the schematic, so that the schematics are going to give a good results and the post layout will be easy to meet the layout or the schematic results, I would say. Once the designs are done with the LVS, TRC and the post layout simulations are done, we are almost ready to send the database to the foundry. So, before going to the foundry, there are other checks that we need to cross check, because we need to make sure how the reliability is there, I mean how it is going to run the circuits in long run. So, there are many sign off verification checks that we need to do. Some of them are EM, electro migration. What does it check is, in a long run there if enough current goes through a single metal, whether it is going to sustain or not. If the current is huge and metal widths are very small, it can happen in a long run, metals can break, so that the reliability can come down. So, you need to make sure electro migration checks are done and IR drop checks are done. IR drop checks, I mean as I mentioned in the starting, each device should have should get the enough voltage and the enough current to turn on the devices well and to get the better results and all those things. IR drop has to be in a minimal way. I mean the you need to, designer will be mentioning the what kind of drop, I mean any circuit or the transistor can be offered and all those things. There are DFM checks that we need to do, design for manufacturability, to improve our yield. Yield is nothing but on a wafer how many, after fabrication, how many good chips that we are receiving, which indicates the yield ratios and all those things. And there are some electrostatic discharge checks. Okay. So, once the ICs are fabricated, any charged body is contacted with these ICs, there is if there is any short discharge path happened from a charged body to a ICs, the ICs can damage. So, we need to do a electrostatic checks where your IC should able to bypass the electrostatic discharge to ground, not to the circuit directly, so that your chips will not be burned when there is a electrostatic discharge is there. Okay. And there are some PERC checks which checks the ESD checks and all those things. Once the designs are ready with the DRC, LVS and other checks, other sign off checks done, we are ready for the tape out. So, tape out is the process of sending the database to the foundry in a GDS format or the OASIS format for the fabrication, where foundries will collect this DB and they will distribute each layer into a masks. They will create a masks and they will fabricate the each layer one after one. There are different fabrication companies, I mean that you know, TSMC, Samsung, Intel, GF, Micron and SCL and 𝗬𝗪. There are many more companies which are fabricating these ICs and all those things. So, IC fabrication steps. Before we go to a IC fabrication, so we will take a few minutes break and come back with a we will come back. Thank you.
తోలుబొమ్మలాటలకు భారతదేశంలో 2000 సంవత్సరాల చరిత్ర కలిగి ఉంది. ఈ కళ ప్రధానంగా సాంస్కృతిక, ఆధ్యాత్మిక దృక్పథాలను ప్రజల మధ్య వ్యాప్తి చేయడానికి ఉపయోగపడుతుంది. తెలుగు భాష ప్రదేశాల్లో దీని పుట్టుక శాతవాహన రాజవంశం, విజయనగర సామ్రాజ్య కాలం నాటికి జరిగిందని భావిస్తారు. తోలుబొమ్మలాట జానపద కళారూపం. మానవుడు స్వయంగా అనుకరించలేని జానపదుడు కావ్యంలోను పురాణాల్లోనూ వర్ణింపబడిన పాత్రల ఆహార్య విశేషాలను స్వయంగా సృష్టించుకున్నాడు. తన భాషతో ఆ మూగ చిత్రాలకు ప్రాణం పోశాడు. రకరకాల విన్యాసాలను వాటి చేత చేయించాడు. తాను స్వయంగా వెనుక నుండి ఈ పాత్రలను కదిలించాడు. కదులుతున్న ఆ జీవం లేని బొమ్మలతో జీవనిబద్ధమైన ఒక దృశ్యాన్ని ప్రదర్శించడంలోనే జానపదుల కళాత్మకత దాగి ఉంది. తోలుబొమ్మల పుట్టుక మీద అనేక కథలు ప్రచారంలో ఉన్నాయి. పూర్వం రాజుల ఆస్థానంలో లేని పండితులు తమ ప్రభువులను సంతోష పెట్టడానికి బొమ్మలను తయారు చేసి మానవులుగా నటింపజేస్తే సృజనాత్మకంగా ఉంటుందని భావించి తోలుబొమ్మలను తయారు చేసి తెల్లటి పంచెను తెర అమర్చి దానిపైన దీపం కాంతిలో బొమ్మల నీడలను పడేటట్లు చేసి బొమ్మలాటలను ప్రదర్శించేవారు. ఈ తోలుబొమ్మలు ఆంధ్ర రాష్ట్రంలో ప్రాచీన ఓడరేవులైన కళింగపట్నం, భీమునిపట్నం, కొరంగి, మచిలీపట్నం, వాడరేవు, కొత్తపట్నాల నుంచి విదేశాలకు భారతీయులతో పాటు వెళ్లాయి. పాశ్చాత్య దేశాలలో జరిగే ఉత్సవాలలో తోలుబొమ్మలను ప్రదర్శించడాన్ని బట్టి చూస్తే ఈ కళకు ఇతర దేశాల్లో బహుళ ఆదరణ లభించిందని తెలుస్తుంది. తోలుబొమ్మలు కాలానుగుణంగా ఆయా దేశాల్లో భిన్న రూపాలు ధరించినప్పటికీ భారతదేశం వీటికి పుట్టినిల్లు అని చెప్పవచ్చు. భారతదేశంలో ఉమ్మడి ఆంధ్రప్రదేశ్, మహారాష్ట్ర, కేరళ, పశ్చిమ బెంగాల్ ప్రాంతాలలో వ్యాపించి ఉన్నాయి. ఆంధ్రదేశంలో తోలుబొమ్మలాటలు ప్రదర్శించేవారు చాలా వందల సంవత్సరాల నుండే తోలుబొమ్మలాటలు ప్రచారంలో ఉన్నాయని నాచన సోమన తదితర కవుల రచనల నుండి గ్రహించవచ్చును. భారతీయ జానపద ప్రదర్శన కళల్లో క్రీస్తు పూర్వం 3వ శతాబ్దం నాటికే తెలుగుదేశంలో తోలుబొమ్మలాట ప్రచారంలో ఉన్నట్లు తెలుస్తుంది. తోలుబొమ్మల తయారీ చాలా శ్రమతో కూడుకున్నదని చెప్పవచ్చు. వీటి తయారీకి జింక, లేడి, దుప్పి, మేక ఈ 4 రకాల జంతువుల తోళ్లను వాడతారు. చైనాలో గాడిద చర్మంతోనూ, గ్రీసు దేశంలో ఒంటె చర్మంతోనూ తోలుబొమ్మలను తయారు చేస్తారు. పచ్చి తోళ్లను పరిమితమైన వేడి నీటిలో నానబెట్టి బండి మీద లేదా చదునైన చాప మీద పరిచి తోలుపై ఉన్న వెంట్రుకలను తొలగిస్తారు. ఆ తర్వాత తోలుకు మిగిలి ఉన్న పల్చటి చర్మపొరను పదునైన కత్తి సహాయంతో తీసివేసి మరోసారి వేడి నీటిలో వేసి ఉప్పుతో శుభ్రపరుస్తారు. శుభ్రపరిచిన తోలును మేకుల సహాయంతో చతురస్రాకారపు చెక్కను బిగించి ఆరవేస్తారు. ఈ విధంగా చేయడం వల్ల మిగిలిన కొద్దిపాటి నలకలు ఉంటే అవి పోతాయి. రంగస్థలంపై పొడవాటి గుంజలపై తెల్లటి వస్త్రాన్ని లేదా పంచెని ముందు భాగంలో గట్టిగా లాగి కడతారు. తెరభూమి నుండి నిలువుగా ఉండకుండా కొంచెం ఏటవాలుగా కడతారు. ఈ విధంగా కట్టడం వల్ల బొమ్మలను ఆడించేటప్పుడు బొమ్మలకు కాళ్ళు అడ్డు తగలకుండా ఉంటుంది. తోలు బొమ్మల ప్రతిబింబాలు సరిగ్గా తెరపై పడటానికి తెరలోపల నుండి పూర్వం కాగడాలు ఉపయోగించేవారు. అయితే విద్యుత్ సౌకర్యం అభివృద్ధి చెందిన తర్వాత ఎక్కువ కాంతినిచ్చే విద్యుత్ బల్బులను వాడుతున్నారు. ఆటలు, పాటలు, మాటలు, మోతలు ప్రదర్శన సంబంధమైన కదలికలకు అనుగుణంగా ప్రధాన గాయకుడు పాడుతూ ఉంటే మిగిలిన వారు వంతలుగా పాడతారు. వంతల్లో స్త్రీలు ప్రధానంగా ఉంటారు. ఇందులో స్త్రీ పాత్రలకు స్త్రీలే పాడతారు. వీరికి హార్మోనియం, తాళాలుంటాయి. వాయించే వ్యక్తులు కూడా వెనుక కూర్చొని వంత పాడుతుంటారు. అంతేకాదు వాళ్ళ కాళ్ల కింద బల్ల చెక్కలుంటాయి. ఆయా ఘట్టాలను అనుసరించి ఈ చెక్కలను తొక్కుతుంటారు. తోలు బొమ్మలాట అంటే చాలు కేతిగాడు, బంగారక్క, జుట్టుపోలిగాడు వంటి హాస్య పాత్రలు ప్రధానంగా వస్తాయి. ఈ పాత్రలు గ్రామీణుల మనస్సులపై విశేషాదరణ చూపుతాయి. పోలిగాడు తెర మీద నుండి తప్పుకున్నప్పుడు అల్లాటప్పగాడు ప్రత్యక్షమై బంగారక్కని ప్రసన్నం చేసుకునేదానికి ప్రయత్నిస్తాడు. అన్ని బొమ్మల కంటే కేతిగాని బొమ్మ చిన్నది. పానకంలో పుడకల తెరపై ఎక్కడో ఒక చోట ప్రత్యక్షమైన శృంగార ఘట్టంలో ఉన్న అల్లాటప్పగాడిని టకీమని ఒక దెబ్బ కొడతాడు కేతిగాడు. వానల కోసం తోలుబొమ్మలాటలు విరాట పర్వంలో దుర్యోధనుడు కురువృద్ధులతో విరాటరాజు గోవులను ఉత్తరం వైపు తరలించే ఉత్తర గోగ్రహణం కథను తోలుబొమ్మల ఆటగా ఆడిస్తే వర్షాలు కురుస్తాయని ఒక నమ్మకం ఉంది.
Hello friends, welcome back. So far we have discussed the VLSI flow, where we started with a spec design and we went to a circuit design and pre-layout simulations, layout design and post layout simulations and all those things. So if anybody has a questions, feel free to reach us. Okay. Hello
sir, good morning sir.
Good morning.
సార్ నా పేరు 𝗧𝗦𝗔𝗧 నేను ఇక్కడ ఆదిలాబాద్ నుంచి కాల్ చేశాను సార్.
ఓకే
సార్ నాది డౌట్ వచ్చేసి సార్, లేఅవుట్లో మెటల్ డెన్సిటీ సమస్య ఎలా సాల్వ్ చేయొచ్చు సార్?
కెన్ యూ ప్లీజ్ రిపీట్?
లేఅవుట్లో మెటల్ డెన్సిటీ సమస్య ఎలా సాల్వ్ చేయొచ్చు సార్?
మెటల్ డెన్సిటీస్.
అవును సార్, డెన్సిటీ సమస్య ఎలా సాల్వ్ చేయొచ్చు?
So what does this metal density indicates is how much is the metals in a particular area it is available. Okay, so there could be like two types of densities. There are like minimum densities and the maximum densities. So minimum densities can be covered with by adding the extra dummy metals. Okay, if there are any maximum density violations, that you need to reduce the unwanted metal so that it meets the maximum metal densities requirements. Okay. So as we discussed so far, we have discussed all the VLSI flow and we are ready for the fabrication. So now let us also understand what happens in the fabrication flow. Whatever we have designed in a layout, the polygons and the rectangles, the contacts and the vias, whatever we added in the layout are going to be fabricated as a directly without anything. Okay, but are the rectangles whatever we have designed are going to be placed as it is, or is there any deviation? Okay, let us understand in a fabrication flow whether the layout that has defined is directly going to be fabricated or some deviations are there. So that is there any other fabrication challenges that we are going to have, so that we can how to mitigate them in a analog layout. Okay. So, there are many steps in the IC fabrication flow. I would like to give brief few of them, some of them are like wafer fabrication, wafer formation and oxidization and photolithography process, etching, doping, metallization, and after all these we need to assemble this and package it to protect our ICs or the dies whatever we have fabricated from the external pressures and the damages. So, what is a wafer fabrication? All these ICs are created from a pure form of silicon, kind of a sand. That sand will be molded into a strong iron rod or a silicon rod, we call it as, called ingot. That silicon rod or the ingot will be sliced into a thinner films which are called it as a wafers. Okay. So, we are going to fabricate all the devices whatever we have designed in the layout on that thin film called wafers. So, once we have the film or the wafer whatever that we have required, so after that we need to design all the layouts. Say from the cross sectional view what we have observed is, on a P substrate we have N plus source, N plus drain, and which is isolated with the gate oxide material and gate material. So, this P substrate, imagine we have a wafer, assume that it has a P substrate wafer. So, or it is doped with the P substrate. So, that P substrate is entirely covered with a gate oxide material, you can see on screen, which is called a gate oxide, which is done with the oxidization process, where a deposition of all the gate oxides is done on entire wafer, and we need to select the or remove the unwanted portions of the silicon dioxide material. This silicon dioxide material will act as a isolation between the devices. So, you need to add a photoresist material. This photoresist material is very sensitive to the light rays. Whatever the light exposed area will become easily soluble, so that you can etch the photoresist material easily, and the visible portion of the silicon dioxide can be removed using a etching process, using a gases or acids, that we can remove the unwanted portion of the silicon dioxide. So, you can see in a third picture where photoresist material is exposed to a ultraviolet rays, the exposed area of the photoresist material become easily soluble. You can remove the photoresist material. Once this photoresist material is removed, the exposed gate oxide material can be easily removed. So, which you can see in a fourth picture where silicon dioxide material presents in the around the substrate, and the same steps can be followed to gate oxide fabrication, gate fabrication. So, again gate oxide will be completely deposited on the substrate, and we are going to add a photoresist material. This photoresist material will be exposed to a ultraviolet rays to remove the unwanted portion of the gate oxide material. This unwanted portion of the gate oxide material will be exposed to the etching layers called wet etching or the dry etching, and using this etching process we can remove the unwanted portions of the gate oxide material. Same steps can be followed for the polysilicon material. Once the polysilicon material is fabricated, we have a silicon dioxide fabricated, which protects the device interconnection between the device to device, and gate oxide is fabricated, which acts as a gate oxide material, and polysilicon is fabricated, which acts as a gate material. The remaining portions of the device is nothing but a source and drains. based on whether it is a PMOS or NMOS, you are going to do ion implantation. So, to convert the remaining portions of the device into a p type material or n type material. So, here I mean since we started with a NMOS transistor, so p type n type implants are going to be added to form a n source and n drain. So, now the cross sectional view of the device, whatever we have observed, the source and drain are isolated by a gate and gate oxide is fabricated, which we call it as a MOSFET. Of course, the n plus region will be fabricated once and the p plus region will be fabricated once. Hello? Hello? Seems to be. Hello? Hello?
Hello.
Hello?
Sir, Chepan sir.
Yeah, can you
Hello.
please ask your question?
Sir.
Hello?
Sir, Chepan sir.
Question please.
Sir, chip fabrication की time ఎంత అవుతుంది? ఎంత time పడుతుంది sir?
So, chip fabrication usually takes couple of weeks. Okay, I mean you can call it as a month or more than a month, but after that packaging and all those things takes a couple of weeks. So, which I mean we can call it as a 1 to 3 months, I mean the whole process can take and you will get a IC2 lab and all those things. Okay. So, coming back to our topic. So, now devices are fabricated with all the gate oxide, gate material and P implants and N implants. So, now we are going to fill with the silicon nitride material to provide a isolation between the device and the metals. We are going to add a deposit a silicon nitride material on entire wafer, and to take the connections from a silicon nitride material, we are going to drill some holes which we are call it as the contacts to take the source connections and the drain connections. Once you have the source connections, drain connections and the gate connections, we can say a PMOS or NMOS is ready to hook up to the next level of interconnection between the devices and all those things. So, the same kind of fabrication steps, oxidization, photolithography process and doping, etching, everything will be followed for the each layer. As we discussed in a 15th slide, there are many layers available on a per particular device like P diffusion, N diffusion, polysilicon and all those things. Each layer are going to be fabricated as a masks, and from that mask these ultraviolet rays are going to be sent to the photoresist material to select the required portion of the materials to be fabricated. Once the devices are fabricated well, we will send it for the packaging, where this packaging will protect our the dies from the external damages and all those things. Once the packaging is done, so there are like many packaging steps used: dual inline package and pin grid package, ball grid package, QFP package, and based on the advantages and disadvantages of the package, I mean the higher level management are going to be used, are going to take the decisions what kind of package can be used. Hello?
Hello sir, good morning. నేను CSE స్టూడెంట్ పర్సింగ్ చేస్తున్నాను సార్.
Okay.
ఇది ఒకవేళ ఒక CSE స్టూడెంట్ VLSI లో కెరియర్ పర్సూ చేయాలంటే డిఫరెంట్ డొమైన్స్ ఉన్నాయి కదా, సో ఏ వర్టికల్ చూస్ చేసుకుంటే బాగుంటుంది సజెస్ట్ చేస్తారా?
Yeah, sure. See, the computer students can also try a chip design, I mean can come into a chip designing industry, but I mean you need to have a fundamentals of basic electronics to come into the picture. I mean you need to have a basic electronics concepts and all those things. Maybe you can start it, you can try as a Verilog design engineer and all those things. And some of the engineers, I mean those who pursued the analog layout course also, but you need to spend some extra time initially to understand the basic electronics and all those things. Okay. I will not say it is impossible to become a computer engineer to a VLSI engineer, but it is possible, I mean as long as they show a dedication to understand the circuit theories, basic electronics, device functions and all those things. Okay. Back to our topic. So, once the fabricated ICs are packed well, okay, which are brought with the external pins and all those things, we can say our ICs are ready for the testing. All these ICs are going to be into a lab and test in under different conditions to make sure the spec is in line with the or the silicon results are in line with the spec that we have defined. Okay. Say on silicon results are meeting with the our the spec defined, we can say our chip is successful. If there are any deviations, that we need to follow the same procedure, we need to go back and retune the circuit and do the pre-layout simulations, send it to the layout, and the layout has to be done, and you have to finish the DRC, LVS post layout simulations and the final sign off checks, and again I mean we need to go for the fabrication. It is like a iterative process that until you get a the expected results, I mean you need to follow the whole process. So, that is why and the chip manufacturing and the whole design involves in a lot of cost and the time. So, that is why I mean we need to be very careful while designing in the starting itself. We cannot take any deviations from the performance. You need to make sure all the functional checks are meeting in the first simulations or the first cut layout simulations and all those things. So, that I mean we can get expect a silicon results are good. Okay. What are the challenges in the fabrication process that as a layout engineer that we should understand and why we should understand. So, just now we have seen all the fabrication process uses a different methods, fabrication of ICs like a wafer fabrication, oxidization, lithography process and all those things. Even though IC fabrication method uses the a finite tools, I mean very precise tools, still there are some issues in the fabrication, because as I mentioned we are using the lithography, etching and doping etc. If what happens, I mean if it is a under doping happens or the over doping happens, what happens if the doping concentrations are high and low, or what happens if the etching process, while etching process if the rectangles are the over etched and under etched. So, that is why as a layout engineer we need to understand the challenges that are going to be faced in the fabrication flow, that we have to mitigate in the layout. So, that I mean our layout whatever we are designing is going to be fabricated well in the flow and you are going to get a expected results. Any devices with a similar same physical parameters or the physical parameters may not have a similar electrical properties in on silicon. Why? Because of the fabrication process and because of the temperature, because of the mismatches in the process variations. The mismatches, what is mean by mismatch? The variations between devices are called mismatches. Mismatches may have a large impacts in a certain circuits, especially in analog, because analog circuits are going to be dealt with micro voltages and millivoltages and microcurrents and all those things. So, it is very important to make sure all the values are improper. You cannot even take a minor deviations from the values. Okay. Even minor gradients can produce a large variations in analog layout. What are the challenges that you are going to see a fabrication? As we said, etching process and the doping process are not so to be as we discussed. I mean there are slight deviations in the fabrication process because of the availability of the tools and the it is a process method itself. I mean it has minor very minor deviations, that I mean we need to make sure to take care in the layout, how to take care in the layout. So, as I mentioned in the design itself, the designer was mentioning the some of the devices need to be taken care with a well matching and all those things. Okay. Because designer already predicted the devices are very critical and those has to be exactly similarly fabricated well or should have the electrical parameters of both devices should be exactly same. So, that is why he mentioned in the schematic, I mean the devices are going to be very important and you need to pay a critical attentions. Okay. So, to match the electrical parameters of a devices, you have a many techniques. One of the technique that we call it as a matching techniques. So, if you do a proper matching, you are going to have a similar parameters or the similar electrical parameters. You can achieve you can target the similar electrical properties. Okay. There are matching techniques where all the devices, I mean the bigger devices, you need to distribute well, so that it exhibits the similar parameters. Okay. When you place the devices side by side, you may not expect the similar properties. If you split the devices into pieces, I mean multiple fingers, and if you match AB BA or AB AB or ABA, all those fashions, you can expect the parameters or the process variations are distributed to all the devices equally, and you can expect a close proximity electrical parameters are same. There are different matching techniques that we use in analog layout, a common centroid method, okay, and where the center of the axis between all the devices should be similar, and a cross coupled common centroid where we keep the devices in multiple rows and multiple columns and make sure the center portion of the matching array is on a similar axis, and there is a interdigitization process where we distribute the devices equally AB method, where I mean you can whatever the process variations that we are expecting equally distributed. What are the different process variations that you can expect on a chip? The process variations can be etching variations, and the oxide thickness variations, and the temperature variations, and the what you call pressure and the physical damage or the physical properties changes and all those things. So, there are many analog guidelines that we follow, not only following only matching techniques. While you design there are particular analog layout guidelines that we need to follow, that make sure the analog designs are going to be good and it is going to be expected to give a good results and all those things. Some of them I would like to introduce here. You need to, as discussed, I mean you need to follow a matching techniques for a critical devices, so that it will have the similar electrical properties, and you need to design the layouts as compact as possible, because the chip area is very costly and you cannot take the bigger areas. So, which is going to be cost of the chip is going to be huge, and if you are optimized in a compact area, your parasitics will be less and you can add additional circuits, that means additional features to your applications, and you need to follow the enough metal widths, okay, enough metal widths to minimize the resistances and to allow the maximum current that it can flow and all those things. And with the latest fabrication techniques, there are like many other issues that we are going to see. So, when I started my career, I was doing a 130 nanometer or so. Right now the technology has shrunk to 2 nanometer, 3 nanometer. Okay. So, you can imagine how many times, I mean, device has shrunk to and how compact the device became. So, during this latest fabrication techniques, we are seeing many other issues like LOD, STI and WPE, length of diffusion we call it as, and shallow trench isolation effects and well proximity effects. So, you need to understand what is exactly going to be happen with these issues and how it is impacting the devices, how it is changing the electrical properties of the devices, how to mitigate them in the layout. Hello.
Hello, sir.
Hi.
Hello.
Hello. Yeah, please.
Yes, sir. I have a doubt. How to identify pure and transistor terminals after fabrication?
So, PMOS, NMOS terminals you are asking?
Yes.
So, we cannot view the PMOS, NMOS terminals on a silicon because it is the dimensions are in nanometers, but you can understand from a layout what is a PMOS and NMOS that is going to be exactly fabricated as you have drawn in the layout. Okay. So, coming back to our topic. So far as a analog layout engineer, I have mentioned we need to understand the design carefully, we need to have a circuit level operation and the circuit level understanding, and also we need to understand the fabrication issues, so that we can do a better layout to give them the first cut results are successful and all those things. So anyone that who want to pursue or enter into a analog layout engineer, that they must have a analog concepts and the basic electronics, device functions, device operations and all those things, and also they need to understand the fabrication issues, so that they can take care of the all the fabrication issues that they are going to see in a fabrication ahead in the layout itself. Okay. So how this analog layout is different from a digital? We know digital circuit designs and the analog circuits. So far we have discussed only analog design, and people might want to know how analog and digital are going to be different. Digital designs always uses a predefined gates, any logic that you can design with a NAND gates, NOR gates or the predefined gates, but in analog it is not like that. You do not have any predefined circuit. A same amplifier cannot be used all places. Everywhere the amplifier spec is changing. You need to design all the circuits from the transistor level itself. There is no reuse of the circuit. Okay. And the design time in the digital circuits can be limited, because you have so many automated tools where it designs the design using existing gates and all those things. But here analog circuits, we, as I mentioned, we are dealing with the microamperes and millivolts and all those things. The designing circuits takes more, and the layout efforts also takes more. And the digital design, maybe we may not able to expect like more frequencies and all those things, but you can here expect a high frequency designs and all those things. And the simplified circuit in a digital form, it is easy, but here it is complex circuits where you will have like n number of transistors in a flat mode, that you need to place the devices and route them. So and also the physical design, digital designs uses, they do the layouts, but they use the most of the times they use the automatic tools which are called PNR tools, where these tools will be placed, do the placement, routing and all those things, but of course you need to be good to handle those tools. Hello.
Sir, good morning sir.
Good morning.
సార్ నాది రీసెంట్గా ఇంజనీరింగ్ కంప్లీట్ అయింది సార్ ఈసీఈలో.
ఓకే
సార్ ఇప్పుడు మీ మాస్చిప్స్ టెక్నాలజీ కంపెనీ ఉంది కదా సార్.
ఎస్
సార్, దాంట్లోకి మనకి జాబ్ తెచ్చుకోవాలంటే నేను ఇప్పుడు దేని సైడ్ ఫోకస్ చేయాలి సార్? వేకెన్సీస్ ఉంటే.
Yeah, so to pursue into a any kind of job into a VLSI domain, you need to have a basic electronics. As I mentioned, you need to be good at electronics, transistor level operations and all those things, and you need to have a digital fundamentals and analog fundamentals. Then you need to go through any kind of training institutes. If there are any campus hirings, of course you can get through a campus hirings. If there are no campus hirings, then you need to go to any kind of institutes that they are offering the VLSI courses and all those things. Once you understand the VLSI domain and all those things, you can take the right path or the right domain that you are interested, and you can pursue a course in that institute, and then you can get a job. You will get into a job. Okay. Coming back to our topic. So all the digital design circuits uses the automatic tools, PNR tools we call it as. They use the place and route automatically, they do the tools automatically, but I mean you need to have expertise to control the tools and guide the tools. But here analog layout, I mean you cannot do any automations, you need to do manually, and because all the designs are very critical, even a minor deviation cannot be accepted in the fabrication flow and all those things, or the analog circuits will not accept the minor deviations. You need to do the everything in a manual format. As mentioned, I mean why analog layout cannot be automated, because they are high degree sensitivity to parameters like temperature, process variations and the lower conditions. Sorry. Required is I mean significant human institution and experience to achieve the optimal performances and all those things, and the designs are very complex in between the with the complex interconnections and the components. What are the challenges in the design flow, IC design flow, in entire IC design flow? Okay. So, not only in analog or digital, everywhere in the IC design flow, because the complexity of the circuits are increasing. Okay. As I mentioned, the technology has shrinked from 130 nanometer to 2 nanometer, 3 nanometer in last 20 years. So, that means the device sizes become like very small and small. Okay. So, that means you can fit n number of devices compared to a older technology. The complexity of the device or the complexity of the designs has increased a lot. The connections or the interconnection between the devices becoming a challenging these days. Okay. Because we are adding a lot of circuitry and the devices sizes has shrink, the performance is becoming another challenging, because all the latest technologies gives the compact area, but again it gives us with a lot of disadvantages of long term reliability and other fabrication challenges and all those things. You need to design a circuits that make sure it performs a great performance and all those things. And design rules, as I mentioned, device are becoming shrink, the drawing rectangles because of the size is reduced, all the metals or the spacings are becoming very narrow now. Okay. You need to design the designs to meet the latest design rules and all those things are becoming a challenging. And the other most important is time to market. You need to design the circuit on time and send it to the fabrication and bring it to the silicon and with the proven results and all those things to capture the market. If we are late to the market, I mean others will be occupied with the market. So, design time is reduced, I mean everybody is wants to reduce their design time to meet the market requirements and all those things. What are the technology advancements, I mean that it happened? Okay. So, in a olden days, I mean we see only MOSFET in a planar mode, where source and drains are placed, all the devices are in a planar mode. Okay. So, all the PMOSes and NMOSes are fabricated with a planar structure. Later in a 2021 onwards, there are other devices came up which are called FinFET, okay, where the fins are brought up to provide the better performance with the better yield and all those things. The FinFETs came into picture. Now, we are dealing with the FinFETs, and also we have a GAFETs in a 2023 onwards, and 1 or 2 foundries, I mean we are designing the GAFETs, and the upcoming, I mean we are expecting CFETs also will come soon in maybe in another couple of years or so. Hello? 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 Hello?
Hello, sir. Good morning, sir.
Good morning.
Hello, sir. Good morning, sir.
Good morning. Please go ahead. Hello? Yeah, sorry, looks like this call disconnected. So, let us talk about the tools. What kind of tools, I mean industry is using? There are standard tools, I mean the available, I mean there are tools available for the schematic design, schematic simulation, layout design and physical verification and all those things. So, most of the industry standard tools I mean Cadence and the, we can call it as a Cadence and the Synopsys are the two key players in these tools. So, schematic has a schematic editor tools, and Synopsys has a custom compiler schematic editor tools, and schematic simulation can be done with the Cadence ADE tools, and using a Synopsys also we can do, which is nothing but a custom sim tools and all those things. Layout design, Cadence uses the Cadence, I mean we can use a Cadence layout editor tools which are called layout editor L, XL, GXL and all those things. Synopsys too have a layout editor tools called custom compiler tools. And as we mentioned, physical verification checks are important. There are tools, I mean available to do the physical checks which are called PVS, I mean using PVS, Pegasus. From Cadence we can cross check the physical verification checks, and Synopsys also offers a physical verification checks using a IC validator, and Mentor Graphics also offers a caliber tools to cross check the DRC, LVS and other sign off checks and all those things. Okay, so next to the important question or the interesting question, what are the different companies available in India, so that I mean engineers who are coming out from the BTechs or diploma or MTech would like to try. Okay. There are many companies available in VLSI. I would like to define into three categories, which are hello, 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 hello.
సార్ ఏఐ ఆర్టిఫిషియల్ ఇంటెలిజెన్స్ ని VLSI లో వాడతారా, వాడితే ఎక్కడ వాడొచ్చు మనం?
See, AI, in terms of AI, VLSI plays a very critical role, because all the VI applications that we are creating needs a hardware structure where you need a lot of memory, lot of high speed computing blocks and all those things. All these are going to be achieved with the VLSI, because you need to have a hardware, I mean you need to have a HBM memory devices and high speed computing circuits and all those things. It needs VLSI must, I mean the VLSI is going to play a crucial role in terms of AI, ML and all those things. Okay. So, coming back to our topic, I mean everybody must be interested in, would like to know what are the companies available in a VLSI domain. So, I would like to mainly divide these companies into three parts. One is a product based companies, and IP based companies and service based companies. The product based companies, they do the complete production. Okay, they do the server IP chips, they do the what you call microcontrollers, microprocessors and all those things. Example Intel, they do a core, I mean and NVIDIA graphics cards, AMD, Samsung, Apple, Infineon and NXP. Okay. These all are the product based companies where they do the mobile processors and the system processors and the audio, video, sensors, all those things, sensing IOs, sensing ICs and all those things. There are IP based companies where these do the some part of the IC, okay, which we call it as a IP, where a particular portion of the IP, like regulators we call it as IP, high speed transceivers we will call it as IP, like SerDes and all those things. IOs, I mean high speed IOs, DDR IOs, GDDR IOs, memories, all these we call it as the IPs. There are companies, they are doing the IPs, which are nothing but Synopsys, Cadence, Qualcomm, AlphaWave, and there are many more companies, they do the IP business. And there are service based companies. These service based companies provides the services to both product and IPs, which are nothing but Moschip, I mean we do a IP, we are also entering into the IP, and but we are doing the services plus services to the product based companies and IP based companies. HCL Technologies, Tessal, Wipro and all these provide us the VLSI IC services to the product and the IP based companies. So, what are the opportunities that we have in a analog layout? There are plenty of opportunities in a analog layout, because as I mentioned, whenever we have a IC, whenever a IC or a device that it needs to be communicated to the external world, you need to have a analog IC, and you need to have a high speed SerDes devices, high speed clocking circuits. There are a huge requirement, I mean, available in analog layout. Okay. What are the eligibility to get into a this analog layout domain? Okay. As I mentioned, anyone who has completed a diploma, bachelor's and master's degree in electronics and communication or electronics and electrical, they are eligible for the eligible to enter into a analog layout domain. How to get into a, how to become a analog layout engineer? What are the possibilities or the opportunities or the ways that we have to get into the analog layout domain? Okay. So, there are ways, I mean, majorly, I mean, that you can get into a VLSI domain or a analog layout domain through a getting place through a campus interviews, campus placements, and many companies, I mean, that they go to a campus hirings for the colleges. Hello.
So what is the current size of transistors used in industries now?
The latest technologies are using a 2 nanometer. Okay. TSMC recently, I mean, offering a 2 nanometer devices. The size of the gate length of the device is becoming 2 nanometer now. Okay. So, back to our topic. So, the best way is to get through a campus placements. I mean, lot of companies go to a colleges to hire the freshers into a different domains. I mean, if you are good at the basics and the you can get through the campus interviews, campus placements, and there are companies offering the internship programs where they will provide a 6 months or 3 months internships. I mean, you can get through them also, and there are like industry standard training companies, like many of them are offering the different training courses that you can select through the different training and standard training institutes also. What are the different institutes offering these courses? I would like to mention few courses, I mean, few institutes that they are offering. There are n number of institutes these days, I mean, offering the all the VLSI courses. Some of them are like MISS, previously it called it as the ISS, Institute of Silicon Systems. Now because we merged with the Moschip, I mean, it is the Moschip Institute of Silicon Systems, where we provide the different courses, I mean, analog layout course and digital designs and the PNR and all those things. There are other companies, other institutes, they are providing these services like Marvin Silicon, RVVLSI, Semicon and all those. I would like to mention, I mean, a few details about Institute of Silicon Systems, because we have been in this Institute of Silicon Systems. So, I would like to give a few minutes information, so that, I mean, if that is useful for engineers, I mean, those who want to enter into analog layout, I mean, they can choose. Okay. So, we started this Institute of Silicon Systems in 2012 or so. We have been training many analog layout engineers from 2012. We have trained more than 700 plus engineers, and all these engineers are working in a top notch companies across the globe, and we also provide the industry oriented training, because all the training sessions are taken by our engineers, those who are working in the Moschip. That means, all the practical issues that we are going to see in real term are going to be taught in the training, and we use the industry standard tools called Cadence tools for the layout design, Cadence, Virtuoso, Excel, L and all those things, and we use the Pegasus tools and all those things. And the course duration is about 3 months. We defined this course in such a way that the theoretical part will be covered. I mean, as I mentioned, any layout engineer should understand the basics of the basic operation of the circuit, basic functionality, criticalities of the design, what is expected in the design, what are the care that we are going to take care in the layout and all those things. And we are also going to give you the different methods or methodologies used in the analog design flow, how to do the matchings in detail, why it is needed, I mean how they are going to be fabricated, what are the fabrication issues that we are going to do and all those things, that how to mitigate them in the layout design and all those things. It is a like entire complete 3 months program, and this entire 3 months, I mean it is a like a full time morning, you can imagine, I mean 9:30 to evening 6:30, 7 o'clock or so. So, we have defined this design or the training in such a way that all the engineers are exposed to different designs. We are going to give them, or we will ask them to train, or we will train them on a standard cell designs, and we are going to give a analog designs like the amplifiers. We are going to practice them. We are going to give them a DAC, a digital to analog converters, 1 PLL, and we are going to give them the what you call practical sessions with the issues and all those things, and we do keep a incremental or the intermediate tests to understand whether they are understanding the entire course or not, all those things. Okay. So, for any questions about the MISS, I mean you can reach out on the phone number and the site, I mean that mentioned here. So, hope, I mean this will be helpful for the viewers, that they can able to I hope, I mean I have given the enough details to understand the analog layout, how it is important for an engineer to understand the design and the fabrication flow and all those things. And I know, I mean most of the electronics engineer or the electrical engineers, they would like to choose their career into a core instead of some kind of software or the different domains, because they would have spent a lot of years in learning this electronics and the circuit functionalities and all those things. So, I would say this is a great opportunity to choose as a career path, that they can come into a analog layout and all those things. Okay. Hoping, I mean this is useful. Thank you so much for giving me this opportunity.